Okay, let's get going. Good afternoon, everybody. My name is Brian Soliday, and I manage sales in the Rocky Mountain region for One Spatial. I'm based out of our Frederick, Colorado office near Denver. I'm joined today by Melissa Ubaldo. Melissa is one of our talent solution engineers, and she's based in our U.S. headquarters in Vienna, Virginia. I want to thank everyone for joining us today to talk about challenges with geospatial data. We'd also like to thank the Montana Association for Geographic Information Professionals, or MAGIP, for helping us organize this presentation. I'm sure we'd all much rather be doing this in Missoula or someplace like Whitefish, but hopefully next year we can all be together face-to-face for a statewide conference. So this afternoon, what I'd like to do is focus on some work we've been doing with a variety of organizations across different industry segments at the federal, state, and local government and the commercial level. We're helping them navigate how they handle the constant changes to the data coming in and dealing with the constant requirements on that data and improve those management processes. So there must be a reason why this webinar attracted your attention. So I want to begin with a quick data quality checkup. Encourage everyone to think about the data quality and data quality management in your respective department of organization. So what is the desired state of your data? Think about where you need your data to be in terms of business requirements that need to be met, the purpose of your data, and the level of quality your data must be in to fulfill that particular purpose across your organization. And then think about where you currently stand with your data. So is it meeting the requirements to serve its purpose? And if it does, are you able to measure that quality by which it serves its purpose? So I just ask you to please think about these data quality issues as we go through the presentation today, okay? For those who aren't familiar with us, One Spatial Inc. is a U.S. company. We're a wholly owned subsidiary of One Spatial Group out of Cambridge in the U.K. The organization began its life about 50 years ago, actually, at Cambridge Labs at Cambridge University. And, Cambridge still serves as our worldwide headquarters today. Our U.S. headquarters is located in Vienna, Virginia, and we have satellite offices across the U.S. Additionally, there are One Spatial offices around the world. They all provide local support and technology implementation for the growing global customer list. One of the keys to our success is a really solid technology partnering approach. So the One Spatial team on a global level has significant experience in ancillary technologies that are key to our joint success, and several of those key partners are listed here on this slide. As I mentioned, at One Spatial, we have 50 years of experience developing data management solutions. So here in the US, we're a little bit newer to the market. We started doing work in the US about 7 years ago, starting with the US Census Bureau. We have significant experience across a number of industries, including federal, state, and local government, transportation and infrastructure, utilities, both electrical distribution and water utilities, and facility management. Here's a display of some of the logos of some of our customers that have come on since that first customer census. Many of our projects with these customers are supporting them with our rules-based approach to conflate, validate, and integrate their data. That data that we help them with could be focused on addresses, next-gen 911, transportation data, utilities, as well as statewide spatial data infrastructure projects. Some of the organizations we work with include the state of Nebraska, where we are working with the state on automating their processes for taking data from their CAMA, or their computer mass appraisal system, and validating the incoming data and operating it and ingesting it within their GIS. We work with a number of GIS departments on building data validation workflows as well. So we were just awarded a multi-million-dollar contract with the state of Michigan to help them, and then Arizona DOT, one of our first customers as well, work with them on their spatial data infrastructure, helping them build automated workflows to ingest updated data by first validating the data coming in, then performing a change detection to find the deltas, and then integrating that changes into their source data sets to maintain proper metadata. Lastly, we're working with organizations to help them on the facility management side, the facility management application. So organizations like Google's Real Estate Worldwide Services are leveraging our tools and services to implement validation of their CAD drawings and assist in easy ingestion into their asset management system, which they use, IBM Tririga. We've also worked with them to help implement workflows to validate their Tririga database directly. So our focus has been with working with organizations on implementing automated tools to perform quality assurance and quality control on spatial and non-spatial data sets, and performing change detection to keep systems up to date. I mentioned one of our first customers was Arizona DOT, and we have about 9 different state DOTs that use our technology. ADOT started working. We started working with ADOT and helping them enhance their data supply chain and helping them in automating procedures to ensure that the data was going to meet their requirements and help them with developing standard processes like change detection. So ADOT has 14 different counties that were submitting updates to them on over 144,000 miles of road throughout the state. And what ADOT wanted to do was really automate that process of taking that in from all those objects and data in from the 14 different counties. So when they receive the data, the first thing that happens is they run it through a standardized QA/QC process to make sure it meets their requirements. And if it does not, then they share that back with the original data submission entity, and I help them identify where specific issues are identified within that supply data. Once the data actually passes the ADOT QA/QC process, it then proceeds into an automated change detection process, and we'll demonstrate some of that in real time here in a little bit to determine what's different about the current submittal versus the current road network that exists in the ADOT database. So we're looking at what was submitted versus what's in our source geo database. The system then provides what we call proposals on how to deal with those changes, such as, is it an addition? Is it a deletion? Is it a geometric reshape of an existing current feature? Or is it just an attribution change? Or is it a variety of those issues, which happens many times? So our One Integrate system is used to help ADOT update the data by a review of those proposals, and then acceptance or denial by an ADOT analyst. So some of the updates can be done automated. Some are held for an ADOT analyst to actually work with and accept or deny. So if it's denied, then the proposal is submitted for further review to really determine whether or not what the system is determined to do with that change is correct. So ADOT's experienced some pretty significant increased productivity and much more efficient workflows when dealing with the data ingest process from their partners across the state. This is a quote from ADOT. What's interesting as well is that same process that they use, they're on the other end of it, because every year ADOT has to deliver data to Federal Highways Administration. So FHWA uses our technology to ingest the data from all 50 US states. So what I'm going to do is I'm going to pass it over to Melissa, and she can talk a little bit more about the technology and processes, and then jump into some product demonstrations. So Melissa, it's yours.
Thanks, Brian. So I recognize that I don't think everybody on the call in here might be in transportation, though that was kind of like our focus slide on there. But in general, we all have very common reasons to develop a different approach to better data management solutions. So going back to those questions that Brian mentioned at the beginning, all those questions matter because there are real-life consequences to having poor data quality and poor data quality management. So if your data is being used to plan capital projects, for example, where there are serious financial costs involved, you can lose revenue from misallocated budgetary decisions based on poor data. Poor data also leads to wasted effort for everybody involved. If you think about all of the hours in production that your team might be spending in correcting or updating inaccurate or incomplete legacy data, that legacy data you don't even know that may have been collected in isolation. When you pass that data along to your users or your customers, they'll be wasting time trying to validate and correct data themselves. And then when they do that, you're likely missing out on the opportunity of that corrected data being shared back with you. So inevitably, they will lose confidence and trust in your data. Apart from financial risk, a very real cost of poor data is putting lives at risk by misrouting emergency services due to address inaccuracies. 4 years ago in 2016, IBM put a number of the costs of poor data quality for the US economy. That number is $3.1 trillion a year. So we've definitely seen many forms in which poor data quality could exist within various state agencies and private organizations, but we've been fortunate enough to have worked with a number of them. But even with their unique business requirements, we can actually apply the same rules-based approach using OneIntegrate. OneIntegrate is a highly configurable rules engine that lets you author your business rules so that first and foremost, you can validate your data by finding anything that fails your business rules. You can connect across the entire enterprise and write rules that integrate your data with other sources, specifically the ones that are supposed to be maintained synchronously. And you can also write a rule to automate how you want your data enhanced or how you want your data fixed, so that the next time you run that data through the same data validation rules, they'll end up conforming to the data quality standard that you've set. So as you're thinking about these capabilities and how much your data can benefit from a process like this, it's definitely challenging to decide where in your current workflow a new data quality tool like OneIntegrate might be most painlessly introduced. This need to have your data quality tools be able to work with your current GIS and geospatial systems is precisely why One Data Gateway has been developed as a solution, which is what I will show you today. So One Data Gateway is part of our Location Master Data Management, or LMDM suite of products. It is a self-service web portal that's built on top of OneIntegrate's rule engine that performs data validation, processing, and enhancement. It's a smart, simple, and controlled way to share data validation rules and data enhancement processes between internal and external users. So I'd like to let's use Next-Gen 911 data rollout, for example. I feel like a lot of people are familiar with that. So we recognize the need for cities, counties, and states to be able to meet the Next-Gen 911 deadline. So we at OneSpatial wanted to help facilitate that. So in-house, we developed a set of rules specifically based on the NENA standards. So let's briefly go through how the state of Maryland has implemented One Data Gateway to assist their counties in getting their data 911 ready. So currently, the state of Maryland hosts the NENA rules on their server, and they ask their counties to submit their addressing data to them by following a few steps. So they are first going to upload the data into One Data Gateway, and they're going to run the data through those rules. If there are any issues in the data, the portal then provides those statistics. You can download that information identifying where those issues are so that you can actually address them. Once you've cleaned your data, you can go ahead and upload that clean data again. And if the quality is at 100% conformance to the NENA rules, One Data Gateway then delivers that data to the state. So effectively, it has automated the data supply chain. So for the following use cases that I am going to use now for the live demonstration, we're going to take a look at how One Data Gateway can be implemented at various stages within a workflow. So the first use case that I'm going to show you here is with LA County. They were facing massive addressing issues, and with data representing a population that is large enough to be the 7th largest if it were a state, manually combing through and looking for inconsistencies between their address points, their roads, their buildings, and their parcels, it will be next to impossible. So what we're going to do here is we are going to validate a sample of their countywide address management system, or CAMS data, and see how we can best coordinate any mismatches between them based on their spatial and attribute relationships. So let's pull up a sample of that data here. And this is a sample of West Hollywood, which we are going to submit for LA County. And obviously, you can use any GIS application that you want or anything that's available to you, but I'm just using ArcGIS Pro here as a preference. So some of the validation rules that we are going to run for this data is based on the expectation that we have for the data that we're seeing here. So I'm just selecting a sample here. And we're seeing that, of course, where a spatial relationship would imply an attribute relationship. So what we're going to do is check that this expectation along with other quality standards actually hold true. We're going to run it through multiple sets of validation rules through One Data Gateway. So let's go ahead and submit this data through One Data Gateway on behalf of West Hollywood, which is a jurisdiction of LA County. So One Data Gateway, some of you guys might ask, it's available in the cloud or on-premise, and what I'm using right now is running on my local. But let's say for the LA County example or POC, let's say that this One Data Gateway instance is sitting on LA County's server. So after logging in here as an authorized LA County data provider, So we're seeing which projects are actually available for me to use or submit on. And these are the projects that LA County has given me access to submit my data for. So we have this one right here, which allows me to make our delivery for either one of these three jurisdictions. But let's go ahead and do one for West Hollywood. So what we're seeing here is I'm able to, so again, the workflow that we're running here is for data validation and correction. So I'm going to hit here and say start my submission. I'm basically going to click and drag my West Hollywood submission and hit continue. So what's going on here is the engine is reading the schema of the entire data set, and it's trying to map the schema to what the rules have been set up with. We're going to see here that it's green. It says it's able to do so successfully, but what if it hadn't? So let's go ahead and review the mapping real quick. So in this step, we can definitely customize how each class gets mapped and each attribute gets mapped across to what the rules are expecting. So I can pick and choose which source class I submitted can be brought into the target class. So you're seeing here how street underscore center lines was mapped across as street segment. And then you can definitely do some customization or any kind of enhancement that you need to do on this step just to make your data fit the schema that this particular workflow is expecting. So if you make any changes, you can definitely save them for next time, so you don't have to do that again. And before that, I do want to say that this step would allow multiple contributors who use different schemas to submit their data to be run against the same set of data validation rules. That way, you as an organization only have to write a single set of rules, and then whoever needs to submit their rules of the same data, all they need to do is run this step by themselves and submit it against the same set of business rules again. So I'm going to head and hit continue, and this is going to kick off the processing of our session. So what we're seeing here is a workflow. A session, you're going to hear me say this a lot throughout the entire demo, is a list of tasks to make up a workflow within one data gateway. So I mentioned earlier that one integrate is the rules engine that's running under the hood of data gateway. We're going to take a look at that in a little bit. But for here, what we're seeing is a session always has to start by reading our data in. And once it's loaded, our objects are pushed through a series of validation rules here. These are the rules that we are requiring the data to conform to. So seeing here that I brought in my address points, my buildings, my PSAP boundaries, my parcels, and my street center lines. And the first set of rules that I have running in here is called our essential geometry checks, which is our out-of-the-box set of rules for one integrate. So these are meant to spot very common issues in geometry, such as spikes and kickbacks. It's typically those kinds of issues that you see during processing, ones that you don't even mean or know that you have made. What I like to note about these essential geometry checks as well is every single one of these rules here were written generically. So it means that they are running against all of the data that's been uploaded. It also means that I didn't have to write multiple versions of the same rule to cover each data layer separately. So now that it's finished with this set of rules, let's go ahead and open it up. We're seeing here again, duplicates, kickbacks, spikes, looking for multi-part geometries. And it ran, every single one of these rules ran on 8,357 features, which is, if you do the math real quickly, it should be the total of the features that we just submitted in here. You're seeing here that you're probably seeing all these colors. You're seeing greens, oranges, and reds. And this is because after every rule has finished running, it gives us a conformance rate. So it indicates the percentage of features that conformed to the rule. So where we're not seeing 100% conformance means we have non-conforming features for that. So in this data set, it looks like we found some duplicates. We found some objects with kickbacks. We also found some spikes. More on the rules that we're running here, we have road checks. So these are these validation checks for roads. One of the things that we're checking for geometries is how well the road network is actually connected. So we're checking for overshoots and undershoots, if other roads contain other roads, if they are actually intersecting at their ends, and all that good stuff. We also have simple basic rules for their attributes, saying that all of our roads should have names, and all of our road zip codes should be a valid integer a value within a range of expected postal code values that we have for West Hollywood. For address points here, we have rules to validate their positional accuracy. So we want to make sure that our address point is within a building footprint. We also want to make sure that it's within a parcel. And if an address point is within a parcel, we do expect that their address information attributes actually match up as well. We also have rules here for addressing. Some of these are related to the NINA rules, as you would expect it. So one of these is in relation to how a road center line has been digitized, we are expecting that there not to be any gaps, overlaps, or any parity switches in their address range values. We also have another one here that checks an address point is actually within the correct PSAP, just as an extra rule in there. Right, so after running those validation rules, I have here other rules that actually clean our data, otherwise known as actions. So we are going to remove our duplicate vertices, we're going to remove our kickbacks, our spikes, and explode any multi-part geometries that we've found. I also have a build topology process in here, and what this does is it aligns our roads and takes care of our issues such as overshoots and undershoots. For address points outside of our buildings, here's how we're going to propose to fix them. So we're saying that if there's not an address point, if there's not a building within 20 feet of that address point, but it does share a parcel with a building, we are going to propose to move that address point to that building. And then once those address points are moved to those buildings, we are going to update it and have the building's ID, type, and source, just to name a few of information. So once you correct it, you can also conflate that data over so that eventually you can also write a rule that says the address point within a building has the same building information. So at the tail end here, before we we reach the end of this workflow, we do have some rerun for our rules here. And what this does is it really allows us to check that the automated fixes worked without having to export that data out and looking through it. So we were able to smooth our data, it looks like, of our kickback spikes, and we also exploded any multi-part geometries that we found. At the bottom here, we are also, well, it looks like we didn't fix everything, but we're going to go ahead and take a look at why those didn't fix up. But we do, ideally though, you would want 100% across the board down here. So to check on those, at the end here, we have the last task in the workflow to export our cleaned up version of that data. And we also have a markup layer here that can drive us to the location of our data issues. All right. Before we check on those issues, I do want to show something in here. So, number one, our processing time is about 2 minutes. And the reason for this high performance, is that the processing time for this entire data validation and correction workflow is in 2 minutes. So the reason behind it is that the rules engine, again, the one integrate engine that we're going to look at in a little bit, is the one that's operating under the hood and has a spatially optimized object-oriented disk cache. So as that data is being loaded in, it is getting automatically indexed. So the performance is not compromised even as I increase the complexity of my rules. The performance is definitely scalable. So in here, I can download the results that we just saw in here. Go ahead and save that zip file. But I also want to look at this auto-generated PDF report here of this session. And what I like about this is, if you need to submit results to someone else somewhere down the line, or you just want to keep metrics for your organization, this gives us kind of like the nutritional facts to see how healthy our data was through that session that we just ran through. So, all right, so we know that we did have some non-conformances left up. So let's look at our non-conformances here and going back to ArcGIS Pro. All right. So here are my markups. Let me bring it up. And again, it is pinpointing, it's driving, it dropped a point on all of those non-conformances that we saw. So it tells me exactly which rule these specific features are failing. So let's take a look at our kickback here. And this is a very tiny kickback. If I zoom back a little bit, you're not really going to see that. An editor would have a really hard time looking for this. If I zoom in a little closer in here, we're saying that I have when Integrate was able to report the vertices that are actually causing this kickback or Z angle on this street segment to occur. So the reason why we want to handle these types of errors at the beginning is because before you process it any further, you do want to make sure that you're not processing it using something in the data that can cause even further damage later on, because this will probably cause an error if you run it through different processes. So in a similar manner, we were able to find and drop a pin on the exact vertex that's causing the spike on this road segment to occur. Now let's take a look at our duplicate features. So in here, by the way, these bookmarks, I just made these bookmarks. These were not generated through One Data Gateway. I just did it so we can look at our non-conformances here more quickly. All right, so we have row markups in here that's saying we found duplicate features. And again, this was found using our generic rules. And really all that rule said was 2 objects in the same class can't have the same geometry. So in here, we're seeing that North Sherbourne Drive and Park Avenue have the exact same geometry, but very different street names. We can definitely reconfigure a rule for roads to say that check that the street names actually are not the same as well. So I did that for our address points, where we enhanced the rule to also take into consideration their attributes. So in here, we found address points that are duplicated. And we're seeing here we have 2 stacked on top of each other, 8716 Ashcroft Avenue. And I already checked this. I don't have any unit information in here. So as far as all the available attribution goes, these look like they're exact duplicates of each other. The non-conformances in here. So in here, we're basically seeing, let me use my zoom in here. It's pretty obvious in here that this is detached and it should probably be snapped. And just to measure how far this went. So it's under 5 feet. What we did was in this rule to check for overshoots and undershoots, we said that if we have the starts or the ends of road center lines that are within 5 feet and they're not intersecting, flag them because we think that they should be intersecting. Let's take a look at the other end of this line actually, because this also is telling us that these two should probably be snapped to each other. They should be aligned. And to check that measure real quick, I always like showing how close that is, or knowing, it's just under 2 feet. So it's definitely a non-conformance in accordance to that rule. Oh, I missed one. So in here, we have non-conformance here for the rule that makes sure, oh, I didn't select that. Oh, okay. So it's saying that because of the way that this data was submitted, we are expecting all 4 roads to intersect, to be split where they intersect. So we're seeing here that the street segment at the top is not broken up where it's intersecting this other guy. So we do have a non-conformance for that. So it's not necessarily invalid for this to occur, but the check would definitely be useful for routing purposes, right? Let's see here. Attributes. Let's go with our attributes next. So site structure address points and our road center lines having or not having valid information here. So very basic. I'm saying that my address point should have a valid number and a street name. We're seeing that it does have a number, but it doesn't have any street name information here. And what's interesting is the neighboring street beside it also got flagged. It says that this road does not have a name either. So it might be that, I don't know, that maybe it was generated from that error. Not quite sure, but it was just, I guess, a coincidence that these two happen to be right beside each other. Oh, sorry, I missed my zip code. I did want to check my zip codes in here. So in this rule, we wrote this rule in a positive language, as in to say what makes the object correct. So by saying that these zip codes have to be a positive integer between an expected range of valid Hollywood zip codes, just go my zip code down here, we found this null zip code right here on this road. So what's nice about we always encourage writing rules in a positive language because it would make for a much more efficient and simple check to say so. If you're stating what makes the data correct as a business rule, as opposed to listing out all the possible values that would make it wrong. So we found that this non-conformance right here. Okay, let's move on to some more of our roads. So definitely seeing here one of these roads where they intersect. This is going south. That one's going north. So it's not a surprise that the difference in digitized direction caused it to fail our other rules, which checks for overlaps, gaps, and parity switches. So in here, let me take a look at these two. So the bottom one goes from, let's take a look at the left one, goes from 1018 to 1016. So it looks like it's decreasing as it goes down. But on the north here, it should continue on to from 1011 to 1069. So there's definitely an overlap between these two address ranges, and also it causes a parity switch from odd to even. Oh, I have another example here for overlapping addresses. So on West Keith, here we go. So let's start from the top right here. So this address is going from 9000 to 9022, goes on from 9020 to 9098. So there's definitely an overlap there between 9020 and 9022. All right. So this check I really like, and it's useful for addressing. And all this rule said is if I have a named road with a valid address range as an attribute, then I would expect at least one, or check that I have at least one address point for which it has the same address information, and it actually has a number that falls within the range of my address range value. So we're seeing here for Rangeley, within my map view, I'm seeing only ones for Melrose and Croft, Clinton as well, which are the neighboring roads, but I'm not seeing one for Rangeley. Now, it's not necessarily incorrect, but it, just something to verify that there are no address points here that belong to Rangeley. Maybe it's a possibility that this road has been named incorrectly. So that's just a nice check to have there. All right, and actually, let's look at one of these examples. So for all of these ones that you're seeing here, they all fail a rule that says the address has to be within correct parcel. So this address point is for 949 North Larrabee Street. 948, sorry, Larrabee Street. But the parcel is just 984 Larrabee Street. So what this does is, because of that spatial relationship, we expected the entire address information to match up. So it's definitely missing the direction there for north. So that got flagged as a non-conformance as well. Address points inside buildings. Let me turn this off real quick. Okay. So in here, we're seeing how I have this address point in here that's outside of my building, even though that's probably that building right there. And this got flagged the same. It just had more than one non-conformance. That's because if you zoom in here, it's actually outside of that building footprint. So we definitely would like to check that out. So I think I do have another one right here. Yep. So in the workflow that we ran earlier, you did see that we did go ahead and automate some of these fixes. So I'm going to go ahead and switch the data sources now so that we can take a look at the results from the rules that fixed our data. So let me switch over from our current input to our cleaned data. All right, so let's start back from some of these. So if these got fixed, we should see that these are actually floating, and we're seeing that it got smoothed out. Our spike is smoothed as well. For overshoots and undershoots, so this is what we did here. We said for the auto fixes, I only want to automate the fixes if it's under 3 foot 3-foot in distance tolerance. So what's happening here is you're seeing that these got snapped in here because if you remember, this was less than 2 feet and this was almost 5 feet. So it did not snap it to where we think it should be. And what I really wanted to demonstrate here is, it's really easy to be writing these rules that would automatically fix your data, but you do want to be careful about, overcorrecting your data because you don't want to cause any kind of domino effect in making your data inaccurate by just willy-nilly fixing it to however big you think it should be. So definitely it gives you that flexibility to take over how much of the data you're willing to automatically fix, as opposed to flagging these types of non-conformances for manual review, which is, I think, it's always a good idea to do that. Let's take a look at some our buildings and our address points. So what you're seeing here is I actually created proposals in here for our address points that were outside of our buildings. And we're seeing here that this address point got the proposal for this attribute point was applied. We were able to move it. And for here, you're seeing it's red. And the reason why it's red is because the action that automates accepting these proposals to say, go ahead and move me to that building, said that before we move it, make sure that there's a one-on-one relationship between the address point, the building footprint, and the parcel. So in here, that those requirements are met. There's a one-on-one relationship between these address points, the buildings, and the parcel. But for here, we're saying that there are 2 possible places for that address point. We're not going to go ahead and assume that that's the building that this address point should belong to. So there's definitely, again, many ways for you to enhance how you want all of these auto fixes to work for you. And just to show you as an example of another way that we rejected some of these proposals, this is the address point that's being asked to move in here on this building footprint, but we're saying that got rejected because there was already one inside that building. So you don't want to introduce more issues if you're trying to correct it, right? So as we improve our data, it's definitely helpful to put a visual on how much we're improving. So I want to show you Data Gateway's dashboard in here. It's nice to see statistics as an organization, how many users are submitting their projects, how well we're doing as far as our data workflow or our data management goes. So let's actually pick out the one we just ran. So yesterday, the days before that, I did go ahead and submit for the other jurisdictions that I had for LA County. So I'm able to compare results between Palmdale, West Hollywood, and Lancaster. We're seeing here what are the top violated rules. It looks like a lot of my data is failing the rule where we're expecting that an address point within a parcel has the same address information. I'm seeing how many submissions are made by day by all these jurisdictions. And I think what's most useful is we're seeing the conformance improvement over time. We're seeing the trends as they're being submitted. So it's nice for an organization to keep track of where they're at as far as, metrics goes, as far as goals go, right? All right, and let's see in here, what else did I want to show you? Oh, okay. So I think it's time to go to OneIntegrate. So I've mentioned earlier that OneIntegrate portal. This OneIntegrate portal has the OneIntegrate rules engine under the hood. So let's have a look at OneIntegrate interface. So what we're seeing here is a session, which is what we use, a term that we use to refer to a workflow of tasks within OneIntegrate. And what we're seeing is the session that has been configured to run for LA County submissions. And this is the task list that we pushed data to complete. We opened our data, we ran the rules, we reported our issues, we fixed some of these non-conformances by automatically applying them, and produced a copy of our clean data. So let's take a look at one of these rules in here to see how these are actually authored or written. Let's take a look at address within building. So in this rule, all we're asking here is we are requiring our address point to have exactly one building footprint that contains it. So while writing this rule, we know that it's compatible with the data that we're going to use it against because the rule author allows you to use a data store as a context. So in here, just any kind of jurisdiction input. So I can select which class I want to work with based on the data that I submitted. And again, I'm able to gain access to the schema of the data that I'm bringing in. So definitely no hard coding in here for any of these rule writings. And I can definitely build onto here and say maybe our other our names should be the same as well, and so on and so forth. So I did mention that we use a data store to help set up our context for our rule writing. So let's go ahead and take a look at our data store. I'm going back to my session and selecting the data store that we used. A data store, let me backtrack a little bit, is a term that we use to refer to any external source of data within one integrate. And what we're seeing here is we did use a FileG database to bring in a schema for LA County's CAMS data, but definitely one integrate does not restrict you to just geographic database file formats. It is in fact data agnostic. So it supports CAD, flat CSVs. You can connect to a database that's sitting in SDE, SQL Server, Oracle, and etc. So we did add in Google BigQuery just a few months ago. So definitely if there's a format in here that you would like for us to work with, we can definitely have a look at that for you. So this data agnostic characteristic brings us to the next use case for Cuyahoga County, which is where the setup does involve bringing in or accommodating camera records stored as CSV files. So one of the data synchronization issues that Cuyahoga County wanted to address is between two departments that are maintaining different information for the same data type. So in this case, it's the tax parcel information from a CAMA system, or computer assisted mass appraisal, and this is data that's coming from their tax assessor's office, and they wanted to compare it with the parcel boundary shapefiles that are maintained by their GIS department. So we are going to use One Data Gateway. That's been for we're going to use a project in One Data Gateway that's been configured to have access to those CAMA parcel information CSVs, and for the GIS department to submit their data through the portal. So let's go ahead and do that. Go to my assignment. All right. So we are cross-checking our GIS parcel versus our CAMA. Start our submission. Again, click and drag our data. Here's my shapefile from Cuyahoga. Trying to map that data across again. All right. So what we're going to see here is I only submitted one data. I only submitted the GIS parcels, but you're seeing that there's actually two open data tasks in here that's reading in the CAM parcel CSV, and one is reading in the parcel boundary submission. So what's nice here is, before you can, or to ensure that you're actually comparing it with the data that's most up to date, and in this case, that would be the CAM parcel CSV, you can definitely set up One Integrate to automatically tap into that data source in such a way that you will only have to submit one other source data, which is the one that we're going to submit. So part of this workflow is before we even start comparing what information is on the CAMA side versus what information is on the parcel GIS boundary side, we are first going to start comparing inconsistencies in just the existence of the unique parcel PIN IDs. So the first set of rules that we have here for the two of them are just making sure that the records and the features brought in all have the unique parcel PIN IDs. We check that each parcel boundary, right here. So after that, we check that each parcel boundary exists in the CAMA record, and for each CAMA record to have a matching parcel boundary. The significance being that parcel boundaries that are not listed in the CAMA system could mean that the county is not collecting any revenue from them, right? So ideally, you would want all of these attributes to match up as well. Grantee and grantor, just as an example here, we're seeing that 36%, give or take, of our parcel boundaries sharing parcel PIN IDs with a CAMA record have different grantee and grantor names listed. So we're assuming here that the information on the CAMA side is more accurate. So we do have an auto fix in here that says, go ahead and update the parcel boundary attributes to match the CAMA. So after that change, I did rerun this rule here, the exact match rule here in O3B, and we were able to increase our conformance rate from 36% to about 64%. So again, we're just we're auto fixing we're being careful about how we're auto fixing everything in here. So let's go ahead and take a look at our non-conformances real quick. So this is the sample GIS parcel information from the city of Lakewood. I brought in my markups, which is all these pluses that you're seeing here. Let's take a look at some non-conformances. So you're seeing here that this parcel pin value, this ID does not exist in the CAMA table. And here we have non-conformances on the grantee and the grantor. So what I'm seeing here really is there's a difference between the way that the CAMA side is recording missing values from the parcel GIS side, which they're recording as N/A. But the way that we are comparing these strings is using a Levenstein distance. And what that does is it gives us, as a score, an integer indicating how many characters between two strings are different. So let's take a look at another example where our match came very, very close. We're seeing here that the CAMA grantee side is Snyder Gerald R versus on the parcel grantee side, which is Snyder Gerard R. So it gave us a match score of 1 because we had a difference between that L and the R. But what I want to show you here is that this calculation can be done on the fly within the rule itself. And what you can do to enhance this rule, if you're going to say that you do not want to go through the effort of correcting any match scores that are maybe 1 or 2 characters off, you can definitely reconfigure the rule to say if it's a match score of 1 or 2, let it slide. If it's more than that, then we should probably review it. All right, so after looking at that, let's take a look at more of I want to go to another one of our use cases because there are many other ways to resolve data sets that are out of sync. And this is one of them is applying change detection processes. So in the case of Collin County, every time they received updates from their local jurisdictions, they would simply pastry cut and replace the road data using their city boundaries. So essentially what they're going to have to do after that step is stitch the data back up along the edges, if you're imagining that. So they were spending a lot of time updating the data this way. And because of that cutting and pasting, they would lose metadata in the history as the process continues. Now, it does seem like overkill to be blowing away all that data and replacing it just to roll out updates, especially, for the most part, you wouldn't really be expecting such dramatic changes in road networks anyway. So they asked us to help them come up with a more efficient solution, which would be to deploy a change detection process instead. So what we're going to do here is we're going to pull in old data and new data together, run them through a set of rules that narrow down where and how they are different, create proposals for those changes, and then apply them. Another processing hurdle for Collin County was having to deal with different schemas, which we kind of already tackled earlier. So just as a pre-step to our input data and our change detection, we are going to run some standard schema standardization as well. So we are going to use OneIntegrate to automate this process of identifying and then updating only what has changed between the two data sets. This process is very, very similar to the process that Brian mentioned earlier, which is what we had done for census. So going back to Data Gateway, okay, here it is for Collin County. So let's submit our input data for Collin County. Again, just clicking and dragging, waiting for the processing and make sure that we actually have compatible rules with our data. Should be finishing in a second. All right, so I'm going to go ahead and hit continue. So in this process, and again, it's our change detection process for our roads. What we're doing here is comparing the old data and the new data, both in geometry and in attribution. And yep, I was just double checking there. So what we're going to do here is determine how these two layers are interacting. So if no changes were found, we're going to call it a match proposal. If their geometries match up but have differences in attribution, we're going to call them a scalar change proposal. If there are slight changes in geometry, we are going to create reshape proposals. If a road wasn't there before, we'll propose to add them in. If a road is not there anymore, we'll propose to delete it. And then once these proposals are created, we're going to go ahead and apply them. An automated rule again to apply them. So let's not sit and wait here to process. It should finish in a few minutes. So let's go ahead and take a look at our results. So here's just a sample for our McKinney jurisdiction. Let me just zoom in here a little bit. Oh, and just to show you what kind of edge matching issues happen in here, it's the 2 versus 1 type of, if you have a dual carriageway, there are 2 different ways in which these are being represented between 2 jurisdictions. So just one of the edge matching issues that also have to be dealt with in here. So I do want to check in first on how we are standardizing that schema. So let me have my road base up, and then my blue is my city input, which is the update data. So in the database, we can see it right here. The address ranges are LF_ADDR, but it was submitted as L_add_from. So we went ahead and standardized that schema. I'm going to go ahead and just pull it up. So now you should no longer be seeing L_add_from. We now have it similar to the road base, which is LF_ADDR. So now we can make a more even, it makes it easier for us to determine the interaction between the 2. So let's take a look at some of these issues. I'll bring in my proposals. So in here, I have a scalar change proposal. And again, a scalar change means that we have a difference in attribute, not the geometry. So we're seeing here that it currently exists in my data as County Road 148, but when an updated version of it was submitted to me, it was now called CR 148. So there's which is an indication of a scalar change or change in name. A reshape proposal, which indicates that the objects are almost the same, but not quite, given some parameters in here. And we do take into consideration, bearing differences and all the other kind of nuanced calculations. So in here, what we're really seeing here is, oh, I turned it off, I'm sorry. So we have a road space that is not intersecting here at the end. It was just short of meeting that. But when the updated data was submitted, you can see that it was actually extended to intersect that road right here. So this proposal was then to say, go ahead and reshape it to match the new one. Delete proposal is pretty straightforward. All we're saying here is that if it's not there anymore, delete it. And for here, what we're seeing is, because again, when we were running these rules to compare how these 2 layers interact, we were looking at differences in distance parameters and how much each angle or each bearing would actually change. So according to how we wrote that rule, we said that these are actually too far for it to be considered as matches. So you can definitely reconfigure that to say, if they are close enough, you can extend how wide you'd like the search to be. We can go ahead and call those matches. So there's definitely multiple ways for you to be able to reconfigure it to your liking. And that's the only reason why you're seeing this mix of adds and deletes between those 2 data sets. All right, let's go back to my slide deck right here. So I just want to do a quick recap of all the functionalities that we just saw one data gateway and one integrate to. And through one data gateway, we've submitted data to test some validation rules against them and receive instant feedback results. We've also seen how it can ensure that submitted data doesn't pollute your master data by only delivering that data that meets the business rules in place, only if it's 100% conformance, only if it's clean. And we've seen how it can roll out updates to enhance your data and keep that current within the organization. So all of these steps help promote data interoperability, which is really the core of having effective data quality management processes. You definitely want it to be an ongoing process of collaborative data sharing. So as long as you understand what you need and you understand what the purpose of your data is, you'll be able to determine the standards by which they need to be maintained, the rules that need to be followed. Because after all, only accurate data is useful data, right? So with that, I don't know if there are any questions, Brian, but I think we do have a few minutes to tackle that if there are any questions.
Yeah, a couple have been submitted. So if you want to submit a question, just go to the question pod. Okay. Well, I think we're kind of coming up to our 1 hour. So One Spatial, Melissa and I, we want to thank you for your participation in today's presentation and your overall support for MAGIP. And please reach out to us directly if you have any questions and you want to schedule a call to discuss some of the items that we covered today in a little bit greater detail. We look forward to working with you. One Spatial, your world smarter.